Hi, everyone. So here we have lecture one on a topic called simple harmonic motion. What exactly is simple harmonic motion? It's the pictures that you see here. It's things that just swing back and forth. So the examples that we're going to talk about, a little kid on a swing. If you guys remember being on a kid on a swing, we're going to go over stuff with that. We have a wrecking ball, a picture of a wrecking ball. And then, of course, just a generic pocket watch. Think about the hypnotists. You're getting sleepy. You're getting sleepy. So, what exactly are the details of these kind of things? They're objects that repeat and they're objects that repeat it should be in an incomplete circular pattern. So, for example, a Ferris wheel does a full rotation. That would not be simple harmonic motion. But the dragon ride at the park where you swing back and forth, the pirate ship one, yes, that would be an example of simple harmonic motion. So the question is, are you doing a full rotation or are you doing partial ones? They have period and frequencies. It takes a certain amount of time to go from here and back. That would be one period from one piece, swing. That's one period, 2 periods, 3 periods. It's the time takes to get back to where you started from. And frequency, you guys remember frequency. Frequency is the inverse of period. It describes how often a cycle can occur. And there are some factors that will influence the period and frequency. And we're going to get to those in a moment. Here's a quick practice problem just to see if you guys are fresh. A wrecking ball swings back and forth 8 times in 24 seconds. There are 2 questions for you. What is the frequency and what is the period? All right, nice job with those. Obviously, if you think about a kid on a swing, we're going to go back and forth between kinetic energy, aka moving energy, and gravitational potential energy because we're going off the ground. In this system, energy is conserved. So you guys understand this part. You guys did really well in this chapter. As you go higher off the ground and you let it go, you're going to swing and you're going to swing at the bottom faster. And you guys probably experienced this as a kid. As your height increased, your swinging through the bottom would actually get faster. So you guys are familiar with that. A kid is on a swing. Their grandparents pull them back so they are 2 meters off the ground. So the question here is, how fast would they possibly go at the bottom of the swing? All right, you guys did a good job with that question. As you may have noticed when you actually did the math, I didn't give you the mass because the mass cancels out. So it doesn't matter if you're a really fat kid or a really thin kid, or if there's no kid on the swing at all. If you hold that swing at a certain height, it will always swing at the bottom at the same velocity. So mass has no influence on how it actually swings back and forth. It's based upon the height determines how fast it goes. So if you actually think about those things, neither of them influence things in the big picture. The period, the time it takes to go back and forth, depends on how long the swing is from the pole to the where you sit, and the gravity. Gravity is pulling you down, so obviously, if there's more gravity, you're getting pulled down more. And the length, if you think about things going in a circle, if your length is really small, it will go really fast. But if your length was big, it would go a little bit longer. So once again, the key about this is that mass doesn't influence the period at all. Once again, as the height increases, the velocity increases, the mass cancels out there. So even though you're going higher off the ground, you're falling faster through the bottom point. So these 2 things cancel each other out when it comes to the actual period. Here is the equation for the period of a simple pendulum. I will give this to you if you guys needed it, if we ever see each other in person again. T squared equals 2 pi, the square root of L over G. So both of those terms, L divided by G, are inside that square root. So if you guys are solving for the L or the G, you do have to do the square root. I'm sorry, you have to square the entire function to get rid of those guys. So please be careful when you rearrange the stuff. T stands for the period, L stands for the length, and G stands for the acceleration due to gravity. And as you guys know, if you know the period, then you can calculate the frequency. So here's our last practice problem in this video. A kid is on a tire swing that has a rope length of 7 meters. Can you guys find the period? And that brings us to the end of our lecture on pendulums. There will be more to come, but this covers the basics of how we do problems. We're going to look at them two ways: conservation of energy with the GPE and the KE, or we're going to use that new equation to find the period, and we're going to go from there. But this concludes lecture 1. Good luck with the rest of the problems, and of course, I'm here to help you if you guys need it.